Today we want to continue practice integrating by substitution, which is our anti-chain rule. This is an anti-chain rule. So we have a function that was a derivative that was found with the chain rule. Integration by substitution undoes the chain rule. So we have an integral of f prime of g of x times g prime of x dx. This is clearly a derivative that was found with the chain rule, because we took the derivative of the outside with respect to the inside. That's f prime of g of x. That's df dg. And then we multiplied by the derivative of the inside with respect to x. That's the dg dx. So what we're looking at here is df dg times dg dx. So what we're integrating is df dg times dg dx. Undoing the chain rule, that just tells us we're going to get f of g, which is what we're looking over here. The technique is to identify what our inside function is, the thing that's in the middle, the df dg times dg dx. We're trying to figure out what that g of x is. Our eyes are getting pretty good at identifying what that function should be, but we have to remember we can't just assume that everything is going to work out. We have to make sure that we're able to make the substitution. So the way we think about it is that w is g of x. This is our inside. This is the substitution that we want to make. This is the substitution that we want to make. Then we take the derivative to find dw. If I want w to be g of x, then dw has to look like g prime of x dx, or some constant multiple of g prime of x dx. So this dw is what's necessary to make that substitution work. If we don't have a g prime of x dx to stand in as the dw, the substitution doesn't work. If we don't have g prime of x dx or a constant multiple of g prime of x dx, then the substitution doesn't work. If we don't have this dw as a factor of our integral, then our substitution is not going to work. This can be different, but only up to constant multiples. So we have to have enough. We have to have the g prime. It can be off by a constant multiple, but that's all we can have. Because we remember also, all x must become w. all the x's have to become w. A lot of the times, we don't need to go through an entire process. We know what's going to happen. That's our intuition taking over. We know what's going to happen. So in our first problem, I didn't even include the 7. When we had the integral of just cosine of 5x dx, we know that the integral of cosine is sine, because the derivative of sine is cosine, and the inside is just a 5x. The derivative of 5x is just a 5. The derivative multiplies by the 5, so the integral divides by the 5. We know this one already. We know this is going to be 1/5 sine of 5x plus c. Ideally, this is all we write for this problem. Even if I say, show your calculations. Your calculation should just be the knowledge that there's going to be a 1/5 because of the 5 in there. Your intuition takes over, you just write this down. The point is writing as little as possible, not writing all the steps that someone else decides you need to write down. But we want to understand how the mechanics work so that we can reinforce where that 1/5 comes from. We know that our inside is going to be w. This is what our intuition was telling us. This is why this 1/5 is there, because we knew that there is something weird going on with the inside, but it's pretty simple because it's just a 5x. So we're thinking that w is equal to 5x. This is the substitution that we want to make. And then we're saying that dw is 5 dx. We look at our integral and we have just 1 dx. We don't have 5 dx. We have 1 dx, not 5 dx. So we have 1/5 of a dw. 5 dx is 1 dw. So 1/5 of a dw is equal to 1 dx. We look at our integral and we have 1 dx, not 5 dx. The recipe calls for 1 dx, but 5 dx is equal to 1 dw, so I need 1/5 of a dw. That 1/5 is the 1/5 in our answer. That's where that 1/5 came from. This integral, and it also, we also highlights what we're actually integrating. The f prime here is cosine of w. Three things that we're identifying: the substitution that we want to make, the dw that we need to make that substitution work, and the function that we're actually integrating. Three things. Three. The next one, I increased the 5x to a 5x squared. What that means is that the dw is going to require an x. So the second problem had this sneaky 7 that actually is just a constant factor, so we don't really care. So we want to see what's going on. Oops, check the chat first. No, the derivative of sine is cosine. So the question was, is it negative sine? The derivative of cosine is negative sine. So the integral of cosine is regular sine. Remember, the derivative of our answer should get us back to where we started. So the derivative of sine is cosine. So in this one, our intuition takes over because we know that we're practicing integration by substitution. So the inside is a 5x squared. That means the derivative is going to be an x. Have I got an x? Yes. That all happens at the speed of thought. We notice that this is a substitution problem. We identify the inside. We see that we have the correct dw to make it go. There's some constants mucking around, but that's fine. And we also see what the outside function is. So because the derivative of the inside with the 5x squared is going to be 10x, we're going to have this rogue factor of 10 going around. That's what we get divided. That's what gets divided by. Ideally, what we write is factor of 7. This is 10 from the derivative of the inside, sine of 5x squared plus c, because we don't want to lose 1 billion points. It used to be 1,000,000 points for not writing plus c, but inflation. And then we check. The derivative of sine of 5x squared is cosine of 5x squared times 10x. The 10 from the 10x cancels out with the 10 in as the coefficient, leaving behind 7x cosine 5x squared, so we know we're right. We didn't even mention the plus c because the derivative of a constant is equal to 0, and we just tack it on at the end. This is ideally all that we write for this problem. But what we want to practice is writing the details down so we can see where all this stuff comes from. We start by identifying the substitution that we want to make. And we've been calling it the inside function. The only thing that's an inside function is 5x squared. Then we take the derivative dw. Derivative of 5x squared is 10x dx. So we notice that we don't have 10x dx, we've got 7x dx. So I'm just going to divide both sides by the 10. And 1/10 dw is an x dx. The 7 is just a constant factor. If it's hard for you to see the x dx is what we want, and this 7 is getting in the way, all we have to do is take our recipe down from 10 people, for 1 dw is 10x dx, and figure out how many dw is 7x dx. To get there, we divide by the 10 and multiply by the 7. If I just take this 1/10 dw and multiply both sides by 7, that says that 7/10 dw is 7x dx. With the constant factors, we're just trying to sort out and make the recipe come out to the correct number of people. Question? Once again, once we identify the inside is going to be 5x squared, the dw is the dw that we need to make that substitution work. And by identifying 5x squared as the inside, that says we're going to be integrating a cosine. So that makes us think we're going to be integrating cosine. The integral of cosine is sine. And that's why we just get to this 7/10. Two ways that this problem could be not substitution. One is if this x is not out there. So if I just have 7 cosine of 5x squared dx, our instinct still says the inside is 5x squared, the outside is cosine. W equals 5x squared is the substitution I want to make. The function I'm actually integrating is cosine. The problem is in that second part. If I want to make the substitution w equal 5x squared, then dw is 10x dx, and we realize we don't have an x to be the dw. We don't have an x to be the dw, and that's what makes this substitution work. We don't have a factor of x in our integral to be the dw. Therefore, this substitution will not work. The substitution that we want to make, w equals 5x squared, will not work. We need to be able to recognize when something didn't work. We wanted to make the substitution w equal 5x squared, but that requires dw of something times x dx. We don't have that factor of x. Our substitution will not work. We have to do something else. The other thing that could happen is that if we have an x, but then we have some other x's that we just can't deal with, we don't have a replacement for. So for example, here we are in the same situation. I want w equals 5x squared to be my substitution, so I'm integrating just the cosine. But we have to consider what will make that substitution work. So we still want to do w equal 5x squared. And then our outside function will be cosine. Let's see if that substitution will work. If w equal 5x squared, then dw is 10x dx. And now we have a problem. There is a factor of x to be the dw, but there's another factor of x that we don't know what to do with. So we do have a factor of x to be the dw, but we've also got this other factor of x. There's two factors of x there, and that messes everything up. Sometimes we can get away with going through our original substitution, w equal 5x squared, and figuring out what that x is in terms of w. So if w equal 5x squared, then x is plus and minus the square root of 5w, or w over 5. Divide by the 5, square root. But now we're integrating 7 cosine of w over w, the square root of w over 5. So 35 cosine of w over square root of w. And we don't know that one either. That just causes more problems. Substitution is supposed to get us to a smaller integral. The substitution is supposed to get us to the point where we're just integrating cosine, but we can't make that happen here. As far as what we need for the dw, the x is the functional parts. The 10, we can get rid of the 10. That's no problem. How's everybody okay? Once we practice the technique, we'll start getting used to seeing whether our substitution is going to work and what the constants are going to be at the end. So if you'll notice that on the second set of notes I put out yesterday were the actual solutions. It would be good practice to make sure that my solutions are correct. You shouldn't trust my solutions just because I wrote them, because I make mistakes like everybody else, like this 7x e to the negative 5x. I think I intended to write on that one 7 e to the negative 5x, because the next one is 7x e to the negative 5x squared, which works just fine. But substitution unavailable for this 7x e to the negative 5x. Our instinct is to say w equals negative 5x, so the dw is negative 5 dx. And this is an extra factor of x, and we don't know what to do with. There are things that we can do with it, but it's not going to get us to the point where we're just integrating the exponential function, e to the whatever. We're not just integrating e to the w because of that x. That means we'd have to do something else. Is that okay? I tried to stick to groups and themes for the problems. So like 1, 2, and 3, you were always just integrating cosine. 4, 5, and 6, the intention was that you were just integrating e to the w. In 7 and 8, you're just integrating a w to the third. 7 and 8 were the 5x plus 1 to the third, and then 5x squared plus 1 to the third. And then in problem 9, I switched it up a little bit and made it w to the negative third is what you're actually integrating. And then in problems 10 and 11, we're just integrating a w to the third again. The thing to realize in problems 10 and 11 is that w was cosine x in the first one, and the second one, w is sine of 5x. There's a lot of extra stuff going on with that one because of the 5x. Any questions? One thing to note is that I use the method that I was always brought up with, which was figure out what your dw needs to be in terms of what you have. So I figured out, I know that the sine of x dx, in my mind, I want to make the substitution cosine of x. I need a factor of sine x dx to be the dw. So that's what I write down for my dw. And then I write a constant times my dw. Your other option would be to write would be the solve for dx technique, where dx is equal to negative dw over sine and have the signs cancel out. I don't know why I'm not really a fan of that. I'm really not sure why I'm not a fan of that, but I don't like that one. But if that's what works for you, then you can be in camp solve for dx. How's everybody okay? Solving, it's weird, the solving for dx thing, because for some students, it is the way. I'm like, oh, here's integration by substitution. And students are like, oh, what? Then I'm like, oh, how about this? Just solve for dx. And they're like, oh, why didn't you just do that in the first place? And then they become experts on substitution. But that's why both. Better to know more things, more ways than just one way. Any questions on integration by substitution? Yeah. So I posted these solutions, even though I tried to fool you by making you think I'm not going to be posting the solutions. And I know you're like, oh, just take the derivative of my answer to check. I've got a different idea for how to check my integrals. Because I have Wolfram Alpha on my phone. So I'll just like ask my phone what will. Incidentally, if you just plug in the integrand, you don't have to do the integral symbol. So if you want to save time, instead of opening up the integral symbol, just type in 7x cubed times the cosine of 5x to the 4. This will give you all kinds of stuff, but one of the things that will show up is the indefinite integral. Any questions? I like that it gives you the graphs. I especially like that it gives you a couple of graphs. One kind of like close up where like some stuff is happening, and then one more interesting one. Because what's happening here is we're replacing our x-axis with a 5x to the 4th axis. So it's going to make infinity show up faster. That's why the graph gets all crammed up, because the cosine wants to just do this period the same all the time. But when you replace x, just counting 1, 2, 3, 4, 5, instead of just counting x on the number line, you're counting 5x to the 4th. So it's making infinity show up faster, and that's why we're getting this compression in the graph. For the most part, when you do trig, well, in this case, if you did trig, you look at changing the period, but always just by multiplying by a constant. You replace your x-axis with a 2x axis, which just makes things go twice as fast, and that's why it compresses down. The distance to infinity is just cut in half. That's a terrible way to think about it, but it's pretty effective. It's just like squishing it down. That's why multiplying by 2, your x-axis is now a 2x axis. And that's why it's different the farther out we go. Because we've taken our x-axis and replaced it with 5x to the 4th. So now it's just taking infinity and cramming it closer. The further along the x-axis we get, the faster we're going through the x's. Notice that it's very wide apart next to 0. Because if you take something less than 1 and raise it to the 4th power, it gets smaller. When you multiply by less than 1, things get smaller. When you multiply by greater than 1, stuff gets bigger. When you take the power of something less than 1, it gets smaller. This is because 1 is in the middle of multiplication. 1 is the multiplicative identity. Multiplying by 1 doesn't do anything. Multiplying by less than 1 makes things smaller. Multiplying by more than 1 makes things bigger. 0 is the additive identity. Adding 0 doesn't do anything. Adding less than 0 makes things smaller. Adding more than 0 makes things bigger. It's all where things balance. They balance at different points. The interesting thing is that 0 doesn't have a multiplicative identity. The additive identity doesn't get to have a multiplicative identity. It's weird that you study all this structure about how numbers work after you've been through all this calculus. But that's the way that we do things, I guess. So in problem 10 and 11, we had to decide whether we're going to substitute cosine or sine. the one in this case, it actually didn't matter all that much. But since there's only one factor of sine in problem number 10, that's why we chose cosine to be the W. Because dW is one factor of sine. And we have one factor of sine. And then it's the reverse in the other one. I've got sine cubed and one factor of cosine. So that one factor of cosine is going to be my dW. I'll be looking at W to the third. Since both are odd, if we're insistent upon one or the other, we could use either. I could have said W equals sine X. I used one of the factors of cosine to be the dW and taken the other two factors of cosine and turned them into sine with the Pythagorean identity. So here's in the category of stupid substitution tricks. Let's suppose we have cosine cubed X times sine of X dx. The strategy we used is to say that W should be cosine because it's being raised to the third power, and dW will just be that factor of sine. So we could be like all W is cosine X, just like we did. dW is negative sine X dx. So negative dW is sine X dx. We did this because that was the most obvious thing to do. Because the cosine is being raised to the third power, that should be the one that's inside. But it didn't have to be this way because both of these are odd powers. So you could be like, oh, well, I don't want to be like all those Brittany and Justin wannabes and do the normal substitution. That's all obvious. You have to flick your hair out of your face and smoke a cigarette. This substitution works just as well. W equal sine X. We got to think, what dW do we need to make this substitution work? If W is sine X, then I need dW is cosine of X dx. And there's no negative attached to it. How do you like dem apples? W equals cosine X. I don't have to worry about negatives here. But actually I do. The question is, I need one factor of cosine to be the dW. I have one factor of cosine, but I've got two other factors of cosine. So what we're looking at, the way we're thinking about this is that we have the integral of cosine squared X. One of these factors of cosine is going to be my dW. Sine is going to be my W. So we got to think, what are we going to do with these extra two factors of sine, of cosine? So now we're like, well, what about these extra two factors of cosine? The reason that we can deal with this is that there is an even power of cosine, and cosine squared is equal to 1 minus sine squared. And this is good because sine is just the W. So this is just going to be 1 minus W squared. So I've got 1 minus W squared. Sine of X is W, and cosine of X dx is the dW. And all this is still being integrated. In this case, both cosine and sine had odd powers. So either substitution would work. It'd be a little bit weird to do the problem in this direction. Because of all the extra stuff that you have to do. Substituting cosine, this means we're integrating w to the third, but now we're integrating w minus w to the third. So when we integrate, we'll have a half w squared minus a fourth w to the fourth plus c. So 1/2 sine squared x minus 1/4 sine to the fourth x plus c. Which doesn't look like cosine to the fourth. Depending on how much trig you remember. Because I can replace the sine squared with 1 minus cosine squared, and I can replace the sine to the fourth with 1 minus cosine squared. So we can just kind of undo the thing that we did. So sine squared is 1 minus cosine squared. And sine to the fourth is 1 minus cosine squared squared. Then we just have to hit this with the algebra stick for a little while. And hopefully cosine to the fourth will pop up. I can fix all of your trigonometry problems that you might have at this moment, as long as I just do this right now. If I just multiply this stuff out, you'll see that it all cancels out. All I have to do is just multiply this out, and you'll see that it ends up being negative 1/4 cosine of the fourth x plus c, just like we intended we were going to get. But I have to do it right now. If I don't do it right now, then you're going to forget about it, and all the trig problems that you have right now are just going to still be in play, and you're just going to deal with them moving forward at the normal rates. So I could solve all of your trigonometry problems right now, as long as I do this right now. So let's fix all of the trigonometry problems right now. Oh, darn it, look at the time. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.